Okay, so in this video, we will discuss the so-called definite integral. Before we do so, let us remind ourselves what is the indefinite integral. So suppose we have a polynomial f of x being x squared minus 1. So let us first recall the indefinite integral. So we denote this integral with the integration symbol, a long stretched out s, f of x dx, and that's a notation. Now if we evaluate, of course, we are looking for a function whose derivative is equal to little f of x. So we usually write big F of x plus c. And again, as I've just said, uppercase f is an antiderivative of lowercase f. So the derivative of uppercase f should be lowercase f. So this is the indefinite integral. So in this case, we would have the integral of x squared minus 1 dx. As we have a simple polynomial, we can use the power rule. So add to 2, 1, you get x cubed over 3 minus the integral of 1 is simply x, and of course plus c, the arbitrary constant of integration. And we can easily verify our answer, right? The derivative of our answer should be the original function, which here is x squared minus 1. If you differentiate x cubed over 3, you get x squared, check, minus the derivative of x will give you 1, check. So we have here an antiderivative of x squared minus 1. And that is the indefinite integral. And we say indefinite as there are an infinite number of antiderivatives because of the arbitrary constant c. Okay, well what is now the so-called definite integral? This is our new notion of this video. Well, if indefinite means that there are multiple answers because of the arbitrary constant, definite here means that we will have a single answer, and it will actually be a real number. But for a definite integral, we have to also specify a range of x values. So imagine you have an interval of x values ranging from a to b. So a and b are fixed real numbers. And we will denote the definite integral very closely to the indefinite integral. So we write the integral sign, f of x dx, so this is the integral of f of x dx, but we give bounds of integration from a to b. And this is called the definite integral of f of x dx from a to b. First question, why are we using a notation that is so similar to the indefinite integral? The answer is that there will be a connection between these two, and a very non-trivial connection. But we'll look at this in future videos. For the time being, we'll denote again the definite integral of f of x on ab in this way, and here's how it's defined. This is simply the limit of the corresponding Riemann sum for f of x on the interval from a to b. The well-known Riemann sum with the limit as n goes to infinity, giving us the area below f over ab when f is positive. So we take the height of the ith rectangle, f of xi, times the width. So if you remember, the width of the rectangle times the height, assuming here for now that f is positive, is the area of the ith rectangle. If we sum the area for rectangle number 1, then 2, then 3 up to n, we have an approximate area to the region under f from a to b. And as we let n go to infinity, we get the exact area below the curve. Again, assuming that f is positive. Quick reminder as to how we calculate delta x and xi. Delta x is the width of the interval. So we have an interval of length b minus a. And we divide this interval into n equal parts. So the width of each rectangle is b minus a over n. xi, the right endpoint of the ith interval is obtained from A by adding I steps of size delta x. So there you have it. The limit of the Riemann sum for the function f over the interval ab is defined as the definite integral of the function, and here's how it's denoted. One comment about this. So far we've only used this expression when f was positive, and we know this gives us the area below the curve, f, from x equals a to x equals b. But this limit of the sum makes perfect sense, even if f is negative. So the question is, well, what does this return if f is negative? Well, think of it. If the value of f at xi is negative, what you have is not the height of the rectangle, but the negative of the height. And if you do the negative of the height times the width, you get the negative of the area. And so whenever you have this Riemann sum and the function is positive, you will get the area below the curve. Whenever f is negative, we will get the negative of the area below the curve. And this is why we call this not the area below the curve f from a to b, but the net area. And the word net here is really important, and I'll illustrate this with a simple picture. So the definite integral of f from a to b, being the limit of the Riemann sum, is the net area below the curve given by y equals f of x over the interval x equals a to x equals b. And from a picture you'll understand why we use the word net. As I've just said, whenever f is positive, we will obtain the positive of the area. Whenever f is negative, we will obtain the negative of the area. So suppose that we have the following graph for f of x. Assuming a and b are positive, it doesn't matter, this is only for argument's sake. Suppose the curve looks something like this. Suppose this is a, and this is b, and this is of course y equals f of x. Then you notice that between x equals a and x equals b, there are three simple regions. Right? You have the first region from a to this point. Clearly this region has an area. We can call this a1. So a1 is a positive number, the area of this given region. Well, we have the other region from this point to this point, which is now below the x-axis. But this region still has positive area. We can say the area of the region is A2. And finally we have the third region going from this point to this point. Again, it has positive area. Say the area is A3. And I really want to stress this. A1 is the area of the first region, A2 is the area of the second region, A3 is the area of the third region. So here, A1, A2, and A3 are all positive. And now, let's see what would be the geometric result of evaluating the definite integral of this function from a to b. So if you ask, okay, I will find the definite integral of f of x dx from x equals a to x equals b. So you can evaluate the limit of the Riemann sum, right? Evaluate f of xi as we've done before, simplify times delta x, simplify the whole summation, then let n go to infinity, and you obtain the definite integral, purely algebraically. But geometrically, here's what you'll obtain. As you go from a to b, imagine stopping at these 2 points. So we'll go from a to this point. Now here, because f is positive, we will obtain the positive area, so positive a1. But now, as we keep going from this point to this point, we will not obtain positive a2. As the function from this point to this point is negative, the definite integral is going to return the negative of the area, so negative a2. And finally, as we go from this point to our endpoint b, now the function is positive, and so the limit of the Riemann sum will return the positive of the area of this region, positive a3. And this is why I use the word net area below the curve. You see, we don't get the total area. When you find the definite integral of f from a to b, if the f looked like this, you are not obtaining a1 plus a2 plus a3. You add the area of the region whenever over the interval the function is positive, and wherever the function is negative, the Riemann sum returns not the positive but the negative of the area, and so the limit returns the negative of the area of the corresponding region. And that is the geometric interpretation of the limit of the Riemann sum when f may be allowed to be negative, which is what we call the definite integral. So there you go. Now, let's do an example with an actual interval and an actual function to see an example of such a case. So we'll take the function f of x being the one we had in the past, x squared minus 1, and we'll take the interval ab to be the interval, say, 0 to 2. And we're going to ask quite simply to evaluate the definite integral of f of x dx from a equals 0 to a equals 2. Well, the definition is simply the limit of the corresponding Riemann sum Before we crunch this out and evaluate, let's look at, again, geometrically, what will this return in terms of the net area below the curve? What we have is a simple curve. It is the parabola x squared shifted 1 vertically down. So, we go from 0 to 2, that is the interval of interest, and f of 0 is negative 1, f of 1, 1 minus 1 is 0, and finally f of 2 will give us 4 minus 1, 3. Not a very accurate picture, but imagine that this is perfectly symmetric from 0 to 1 to 2, and now you see that we have two regions. There's the first region here, between the curve and the x-axis. So suppose this region has area A1. And we have the second region from 1 to 2. And suppose that this region has area A2. Both, again, A1 and A2 are positive. They are area of regions. And we know that the definite integral of f of this curve over the interval 0 to 2 will return not a1 plus a2, but as this is a net area, what we'll get is negative a1, as here from 0 to 1 f is negative, so this will return the negative of the area. But as from 1 to 2 the function is positive, the integral will return the positive of the area of this region, so positive a2. So once we crunch out this Riemann sum and the limit, the end result geometrically will represent the difference in area from this region and this one, a2 minus a1. Let us now do it algebraically. Let's evaluate and see what the final answer is. Well, we need to find our delta x. This is b minus a over n, 2 minus 0, 2 over n, just 2 over n. And xi is a plus I delta x. A is 0, so that's 0 plus I times delta x. So it's 2 over n times I. We need to evaluate f at xi and then simplify. Well, this will be very short. We are making a substitution. F of x is x squared minus 1 for any x. We are replacing now x by xi. So we'll get xi squared minus 1. And if you replace xi by 2 over ni, so you square this, you get 4 over n squared, I squared, minus 1 stays minus 1. So now we have our delta x, we have our f of xi simplified, we can evaluate the Riemann sum. So we replace f of xi times delta x 2 over n. And now we know how to proceed, right? So step 1, we're summing with respect to I, so 2 over n is fixed. We can pull this out of the summation. And here I'll be slick. I'll do two things at once. Once my 2 over n is out of the sum, I'm left with summing over the difference of these two terms. Well, property of sigma notation, I can sum these terms and these terms individually and then subtract. So this will be first the sum of 4 over n squared, I squared, minus the sum of 1. So I'm doing two things at once here. Second property, or I should say first property for the second time. Again, we're summing with respect to I, so we can pull out the 4 over n squared, as there is no I, so this is once again a constant. And then we find ourselves with our, or at least two of our fundamental sums, right? The sum of 1 we can sum, the sum of I squared we can sum, so let's replace each sum by its respective shortcut formula. If you recall, the sum of I squared from 1 to n is n times n plus 1 times 2n plus 1 over 6. Minus, well this one is easy, if you add 1 n times you get n. And that's it. Let us now simplify. So what can we cancel? Well, here it's nothing, it's just the n. Now here we have an n over n squared. We can cancel one of the n's. And for the constant terms, 4 over 6, common factor of 2. If you cancel a 2, you're left with a 2 on top over a 3 on the bottom. So that's 2/3 times n plus 1 over n times the 2n plus 1 minus the leftover n. And as before, we're going to bring in the 1 over n multiplying the whole expression, and then we'll essentially be done. Leave the 2 outside, constant multiple. And of course the over n will pair it up with the second function of n here. So we'll have 2/3 n plus 1 over n times 2n plus 1 over n, coming from the over n here, but we multiply everything by 1 over n, so this will be minus n over n. And now we will divide each term, n plus 1, 2n plus 1, n by the n, and we'll have then a trivial limit. As n goes to infinity, we know that 1 over n goes to 0. So what are we left with? Well, 2/3 times 1 times 2 minus 1, which gives us 2 times 2, 4 over 3, so 4/3 minus 1. We want to subtract, so I'll write 1 as 3 over 3. 4 minus 3 is 1, times 2 is 2, and so the final answer is 2/3. That is the value of the definite integral of the function x squared minus 1 on the interval from 0 to 2. The answer is simply 2/3. So this was obtained algebraically as a limit of the corresponding Riemann sum, and geometrically we know this does not represent the area of a single region, but a difference of areas, right? This is the area of this region. So this one you can evaluate with a given Riemann sum. For this function from 1 to 2, you could find the area A1 as well with the Riemann sum from 0 to 1 then negate. And if you were to find A2 and A1 and did A2 minus A1, you will get 2/3. And that is our definite integral. There's one thing though that might seem strange here, is why are we using this notation to represent the limit of a Riemann sum? There's a very good reason, and let's see why now. So I'll draw the picture for f of x, and I'll be assuming that f of x is positive just for argument's sake. The argument is the same if f were negative. And suppose it goes from x equals a to x equals b. Okay, so here from a to b, the function is positive. So when we evaluate the integral of f from a to b, we will get the positive area of this region. Why the notation? Well, let's look at it. We are saying that the area of this region, I'll call it uppercase A, as f is positive, is denoted by integral from a to b of f of x dx. And I claim that this makes perfect sense in the context of area. This is the perfect notation. Well, let's see why. If you remember, for the width of an interval, we use delta x, right? As the width of a rectangle is a small change along the x-axis, therefore, change representing being represented by delta, so this means a small change in x. Now, we know that to get the exact area, we have to let n approach infinity. But if you remember, delta x is the length of the interval over n. And as n goes to infinity, b minus a being a constant, b minus a over n will shrink to 0. So this will approach 0 as n approaches infinity. As we take more and more rectangles, the width, delta x, of an individual rectangle shrinks to 0. And you might think, well, what would be a good choice to represent a really small change in x, a change in x that approaches 0? Well, in the limit, as delta x shrinks to 0, delta x becomes dx. What dx stands for is an infinitesimal change in x. By infinitesimal, we mean the limit of delta x as delta x goes to 0. So when we say that dx is an infinitesimal change in x, think of it as an arbitrarily small change in x. And now we can make perfect sense of f of x dx. Imagine, or remember how we obtained the exact area below the function f. We found the area of several small rectangles, and as we added up the areas of the rectangles, we obtained an approximate area below the curve. And as we let the number of rectangles tend to infinity, so their width shrink to 0, we get the exact area. Imagine the following picture. At any given point x, take a very tiny rectangle. So a very small, narrow rectangle. And you might ask, well, okay, what are the measurements for this rectangle? We have to take, to get the exact area, a rectangle whose width shrinks to 0. Well, what would be a good letter to represent an infinitesimal change in x? That is dx. So we think of our rectangle having width dx. A little width in x, but that width shrinks to 0. And of course, at x, the height of the rectangle is simply the value of the function at x, right? The height will be f of x. So we have a rectangle now whose height is f of x and whose width is dx. So let me rewrite this out, but now backwards, and you'll see why it makes perfect sense. And why we use this sort of long stretched out s. You say we want to obtain the exact area below the curve y equals f of x from x equals a to x equals b. Well, the idea is we must find the area of an infinitesimal rectangle. Well, the area will be the height of the rectangle, f of x times its width, dx, an infinitesimal width. But this is simply the area of one tiny rectangle. To find the total area under this curve, we have to add up the area of all of the other tiny rectangles, but adding up is the same as summing, and so we use a long stretched out s to represent a sum. So now we are saying add up, sum, all the areas of the rectangles, and we're summing from where? Well, x must start at a, and x ends at b. And that's it. So that's why we use this notation, and you can see now, hopefully, that this makes perfect sense. To find the area below f, we find the area of an infinitesimal rectangle, being f of x times dx, that is the area of a single rectangle. To find the total area, we have to sum the area of all the rectangles, starting from a, ending at b. And hopefully now this notation seems a lot more intuitive. One last comment, again, remember that if f were negative, we get the same explanation, but except we don't get the positive of the area, but the negative of the area. And that is the definite integral. And hopefully now the notation makes perfect sense. One last comment are, what are the properties of this definite integral? We have properties of the indefinite integral, and we'll see that we have essentially the same properties with a few additional ones for the definite integral. So here are the properties, and because the definite integral is the limit of the Riemann sum, whatever properties limits and summations do possess, the definite integral will have the same properties. Just remember that delta x is b minus a over n. This will be important for one property. So the first property, so here properties of the definite integral. Property 1. Very simple property. If you integrate any function f from x equals a to x equals a, what is the answer? Well, think of the picture. If x goes from a to a, you have no area, you just have a vertical line. Well, the area of a line is 0. And so the definite integral of f from a to a is equal to 0. That's it. Property 2. Well, because you can sum over a sum individually, and the same goes for a limit, The same goes for the definite integral. If you integrate from a to b, the sum of f and g of x, you can split those up. You can integrate first f from a to b, and then add the sum being the integral of g from a to b. Of course, the same holds true for a difference, so you could imagine that this was a negative, and this would be also a negative. Well, if you remember, we can pull out a constant term out of the sum and also out of a limit. So, the definite integral has the same property. If you integrate from a to b, say k times f of x, and k is a constant, we can move k outside the definite integral. So all very familiar properties. 2 and 3. Property 1, again, thinking of the area, also is very trivial. The area of a line is 0. The last property, which is a bit more subtle but also fairly easy to see, what if we change the order of a to b? Instead of integrating f from a to b, what if we go from b to a? Let's see what possibly changes. So if you integrate f of x from now b to a, and you ask, well, what about the difference between this integral and the one from a to b? What is the difference? Well, look at both cases. In both cases, the delta x. In this case, delta x will be b minus a over n. In this case, delta x will be a minus b over n. And if you ask, well, what's the relationship between this one and this one? Well, factor a negative from this one. What do you obtain? You get negative of b minus a over n. So you see the delta x in this case is the negative of the delta x in this case. And that's all that changes. As the function is the same in both cases, f of xi will be the same. The difference as you go from a to b, then b to a, the delta x becomes negated. You can factor your negative outside, and you get the negative of the other integral. So if you integrate f from b to a, then you change the order of the bounds, you get the negative as the delta x is negated. And that's it. Those are your 4 fundamental properties of the definite integral. There is obviously, or at least there should be in your head, one last question. Why did we use a notation that looks so familiar, so close to the indefinite integral, right? We just justified here from the idea of the area that this notation makes perfect sense. But if you go back, why are we using a long stretched out s then for the indefinite integral? Right now this might look strange, but we'll look at this in future videos and you'll see that there's a very good reason, as there is a very deep connection between the definite and the indefinite integral.